Good morning, ladies and gentlemen. Our next topic of study is current electricity. So, when we actually talk about current electricity, we first have to talk about, well, what is actually moving through the wires. Of course, we've already learned in electrostatics that it's only electrons that really move around. Protons aren't allowed to move. However, way back in the day, when Benjamin Franklin first discovered the idea of electricity, no one really knew what a proton or electron was at the time. They just knew that there are two types of charges, positive charges and negative charges. So when he was theorizing about what was flowing through the wires, he took his best guess. And Benjamin Franklin guessed positive charges. Of course, that's not true, but for hundreds of years, we believed it to be the case. So even now, in our course of study, we call this conventional current. And with conventional current, which is mostly what our work is going to be about, you just have to understand it really ends up being the exact same results as electron current. It's just two different ideas. So if you connect a 1.5 volt battery to a light bulb, normally you take a wire from one end, connect it to the light bulb, and you connect the other end to the negative terminal, the anode. If we were to say that positive charges are flowing through the wires, then positive charges will just be flowing in this direction. They flow out of positive, and they go into negative. But if we're talking about electrons, the electrons simply go in the opposite direction. So when we do our work, it ends up being the exact same result, no matter what direction we choose. So we are going to be using conventional currents. However, it is a bit cumbersome to sketch these batteries and light bulbs with a picture every single time. So let's just go over some basic schematics just to make sure we understand what we're drawing here. A battery is another name for that is a potential difference. It's always going to be represented with long, short, long, short. You have a negative side of the battery and a positive side of the battery. Anything that uses up electrical energy is what we call a resistor. In this case, our resistor, of course, is the light bulb. And resistors are simply represented with a squiggly line. Okay. Of course, these can be drawn in a vertical manner, just as the batteries can be represented in a horizontal manner over here. So here we have our basic schematic of an electrical circuit with our potential difference and with our resistor. Let's define a couple of terms here, okay, just to better understand what these things really are. We saw an electrical circuit, but what exactly is a battery? Okay, what does it mean that there's a potential difference of 1.5 volts? I've previously explained that electric potential is like height, where you have, in this case, if you have a potential difference of 1.5 volts on top of a positive 0.75 volts, on the bottom of a negative 0.75 volts, it's just two different heights. And what a battery is, it's like a charge pump that brings the charges, or really the electrons, to a higher potential. And after it brings them to a higher potential, it basically lets them fall down, like here. So we see the battery raising our positive charges in our conventional current up to a higher potential. And that energy, which is gained from being raised to higher potential, is then used up in the resistor over here on the right-hand side. And the reason electrons move in the direction they do is that every battery ultimately also creates an electric field inside the wire. We previously talked about electric fields being created by single charges, especially if we have a positive plate and a negative plate. And we know the electric field goes out of positive into negative, and a positive charge will feel a force in the same direction as the electric field. Now, when the battery, the electric field line basically runs inside the wire, so therefore the positive charge feels a force and goes through the entire wire itself as it falls from higher electric potential to a lower electric potential. And next we'll look at how combining batteries together increases the electric potential.
To increase the speed of a battery-powered motor, you should wire the batteries in series. That means the positive terminal of one battery connects to the negative terminal of another. The more batteries connected in series, the higher the voltage. And a higher voltage will make the motors go faster. In this example, maximum speed is reached by wiring all 4 batteries in series.
And we can see that overall that you have a combined electric potential, a combined height for the electrons to fall through, which generates more energy. And ultimately understand that in every battery you have an anode and a cathode. You have a positive end and you have a negative end. This is a quick cut open diagram of the battery itself. Whenever you have electrons going through a current, or going through a circuit, understand that when the charges leave, they're going all the way around, which means that the battery is never actually becoming charged. For every charge that leaves, for every electron that leaves, another one enters in on the other side. And the batteries eventually die out when you have inside material, all those charges get used up because they've all gone all the way around the circuit into the other material. Okay? And that's how a battery works. Next, we'll look at actually what is our definition of electrical current. Current is defined as the amount of charge that passes through a point each second. The variable that we use for current is I. I is current, Q is charge, and T, of course, is time. The unit that we use for current is amps, or nearly amperes. So the formula we have is I equals to Q over T. So when we take a look at our next picture over here, okay, we have our device for measuring called an ammeter again. We can see that. And an ammeter basically detects how much charge is passing by each second. So in this case, when we have the charge of the positive charges running and going through, the ammeter detects simply how much charge passes by at any given point each second. So if we were to do a quick practice question, a current of 2.5 amps passes through a wire for 4 minutes, which of course we're going to convert into seconds. 4 times 60 is 240 seconds. They ask us how much charge is flowing through. So if we use the formula I equals to Q over T, Q is simply equal to I times T, which equals to 2.5 amps times 240 seconds, which is equal to 600 coulombs. The second part of the question asks us, well, how many electrons is 600 coulombs really? Well, you just simply have to do a conversion factor. 600 coulombs over 1. 1 electron is equal to 1.6 times 10 to the negative 19 coulombs is equal to 3.75 times 10 to the 21st electrons. a tremendous number of electrons. So if we look at our few conceptual questions we have below, understand that whenever we talk about current versus electrons, current is simply the flow of electrons. It's the electrons that are actually going through the circuit itself. And when we talk about the resistors aren't using up electricity. You can't use up electricity. But the resistors do use up electrical energy, meaning that as the electrons are running through, they're using the energy of the electrons moving. And to better understand what electric potential is and what potential difference really is, here's a couple of questions that really help us understand it. Why can birds perch on high wires without getting shocked? Because the fact is, if there was a downed electrical line, meaning that if you saw normally between two poles, we have wires, we see the birds happily on the wires, and they're perfectly fine. But if a wire happens to be down, and you're walking by, and you happen to decide to pick up the wire, well, you get shocked. So why is it that birds can perch on the wires perfectly safely? Take a look at this video. Okay. In this video over here, we can see the linesman sitting on the line perfectly fine. And the only reason he's able to do so really is because he's wearing a suit that basically is a Faraday cage that protects him from the voltage. But the fact is, when a bird sits on the line, the 2 points of contact, even though there might be 10 million volts running through, okay, each point that the bird is touching is equal to 10 million volts, meaning that overall, is there any sort of potential difference between the 2 points? 10 million versus 10 million means that delta V is equal to 0, and electrons won't want to flow through any sort of charge that's 0. The helicopter, on the other hand, has a different potential, which is why if the linesman were to touch the helicopter normally, then the linesman would get shocked because of the potential difference between the wire and the helicopter. What the linesman is doing is that he's charging up the helicopter. So that way the helicopter ends up with an electric potential of 10 million volts also, which is why then he can, once the helicopter is charged up, he can walk over to the helicopter and get on perfectly fine. Okay. So in the end, understand that when a person touches a wire that's on the ground, ground always means 0 volts. So if you have a wire that's even with a voltage of 100,000 volts passing through, and you happen to be walking by, that's a tremendous potential difference, and then the electricity will happily flow through and happily flow through you. Okay? So squirrels are fine, birds are fine, high up, but not if the wire's on the ground, then it becomes trouble. That's why whenever we see signs, warning signs near power plants, they always say danger, high voltage. Because in the end, we deal with high current all the time in everyday life. Every outlet has enough current to kill you 10 times over. But we're safe for the most part because they deal with every outlet is really 120 volts. That's a very low voltage. The electricity won't just jump out. But if you're dealing with wires like what the linesman was dealing with when you're dealing with 10 million volts. The fact is that the electrons will jump, and they will jump through you. Also, understand that when the electrons are flowing through the circuit, I know electricity seems like it's instantaneous, it's near speed of light, fast. But did you know that electrons are only going to have an actual just speed of only maybe a few millimeters per second? They go very, very slowly through the line. So how is it possible that the electrons can instantly turn something on? When you turn on a switch, the light turns on immediately. That's simply because every wire is already filled with electrons. Over here, if you think about it, okay, when there's a charge being applied, one electron is going to push the next, push the next. The wire is filled with electrons already. So one electron is going to push the next, push the next, push the next, push the next. So it ends up being a giant chain reaction. So when one electron comes out, one electron immediately gets pushed in. Okay, so it ends up being a giant chain reaction of electrons, and that's what current is.